Okay, everyone, this is Roger, and you are my outstanding friends. And we are going to start to investigate what science is all about. What is physics all about? What are these things that are what appear to be body parts that are made out of mud? How did that happen? How did Petra get to be the way it is? Before we can even start to think about how these things happen, how a goose would turn into stone and the feathers and everything become fossilized as a stone when it was once a goose. And how can we find all of these different body parts and so forth and these feet from creatures we never knew about that existed, and I call them no-toes. We have a ton of information about a ton of things. However, a lot of this is not accepted because they don't understand the chemistry and the physics and the bonding and nucleophilic substitution that stabilizes volatile chemistry, which would otherwise deteriorate. I have done this and I understand the process. I'm deep into chemistry and I have recreated the same process. Now, let's start with what actually the particles are that make up everything, because that is not correct now. The Bohr theory of the atomic nucleus is not correct. The atomic nucleus is a dipole. It is not a big, huge positive. And I will demonstrate that in extreme detail because I have the physical evidence to show. Okay, before we even start, let me just explain to you, we can see these interactions with a cell phone, a smartphone. There's nothing special that we're doing. These phones, when they see these, they're using the same device as the smartphones. And here it is, back in 2014, they used the smartphones to look at cosmic rays. Right? They use them as cosmic ray detectors. And here's the thing where it's somewhere down in here. It says that, here's right here, the apps basically transform the phone into a high energy particle detector. That's why you can see all these high energy ones. You won't see anything that's not high energy, explains Justin Vanderbroek, University of Wisconsin-Madison assistant professor, researcher in the Ice Cube project. Particle Astrophysics Center. It uses the same principles as these very large experiments. And all it is CMOS. I understand this very well. It's complementary metal oxide semiconductor silicates. And they produce these extremely crisp images of extremely high energy particles when they collide with these complementary metal oxide semiconductors, and they pick them up and they energize them as a little tiny particle, a pixel, and then they create the display of them based on the energetic values, as you will see here. All right, so these are the ones they're talking about, cosmic ray air showers, and these are a 1 trillion volt proton hitting the atmosphere. Now, protons are gigantic. They're 1,837 or so times bigger than an electron, neutrino, which we're showing as the light particle. A proton is a gigantic piece. That's why you get these showers, because they hit head on to something else and just tons of those particles come off. Now, we have the same particles here. They're basically the same particles. All right, and we can actually see the Higgs fields as they come at us and collide with the atmosphere. Here, it's straight electron neutrino showers. And there's muons involved in this too. You don't see them with the green. Well, you do see them with the green, but you don't see them as divided. Well, actually you can see some here. You see the little black balls? See the little black balls trying to get together? Yeah, I can see them. Yeah, you can see them all over the place, actually. It's just that they're not as conspicuous as they are with the red. Plus, this is not perfectly aligned with the Venturi. You can see how it's splashing off to this side. We just got lucky. Rod Warren did these experiments, and it just got lucky. He just got lucky. And when I saw what he was doing, I said, let's dig deeper. And sure enough, he kept providing me with stuff. Even like today, I just noticed these little black balls are here. It's crazy. Now, you can see the black ones are pushed to this side, and there is none over this side, it doesn't look like. Is that another way we can divide this matter up? You see all the little black ones? They're trying to get them back together with the white ones. That's the key. The black is the only thing they do is attract the white. Let me show you how they work with the red, because in red we can see much, much better. Okay, the red are a much slower cascade of particles, and so we can see them a little better than the green, but they're still the same. They make the Higgs fields, only they're more conspicuous. You can see them much better. Hold on, and I'll show you how we get to these particles here, how the light starts. Well, let's just take it one step at a time. Here's the way the light starts. Let there be light. Back here is the red pulsed laser. Boop, 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 and they come shooting this way. They're waves, and they don't make this elongation and the particle separation and explosion here until they approach the Venturi. Prior to that, they're just waves. And here they are right here. Let's see. Oh, here we go. That's it. That's it. That's all that would happen. They're concussing with the particles that are in front, yes. Because somebody's got to get out of the way. Every one of them has a field, and when a field pushes a field, you get a glow. When there's no push to a field, there's no glow. There's no pushback. There's no bounce. So you don't see any light. That's what light is a pushback to a shove. You push and I shove you back, and that's what you see as light. And it depends on a particle that it hits, how much it bangs back. It's just like hitting a real weak string and going bloop and popping back, and hitting a real bing and it pops back about a zillion miles an hour. That's string theory basically, and it's not far from right. Now here's what CERN wanted to see, and Fermilab. They want to see a muon neutrino, which is the black ball. And they want to see electron neutrino, which is the white ball. And then together, and then they want to see them turn into a muon, which never changed, and then the electron shower makes the shower. This is not my little thing. This is from CERN. Now, that's exactly what we did here. They were attached together. I'll show you them approaching the Venturi and then splitting. That's fission. They came back together here and turned back into light. That's fusion. Now, this is subatomic. This is not atomic, where you have atoms fusing together, forming and being all little bits and pieces and coming back together, releasing a lot of energy. Different story, but it's on a smaller scale. That's all. This is light. They're using photons. Photons are 1,839 times bigger than the particles we're talking about here. Okay, that was my mistake. They are using protons, not photons. We're using photons. Photons are back-to-back electrons, and an electron is 1,839 times smaller than the protons they use. So they got splashes of things all over. They're digging through debris and missing the true components of what they're trying to look for is the smallest bits and particles. Okay, remember I showed you there was a pulsed red laser, bip, 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 making these waves. Well, these are those waves, and these are the particles inside the waves. And they are heading this way to crash into the Venturi, where the black and the white separates. This started out with this is an exact same laser. Bip, 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 bip. And Rod got it worked out where he using all these apps or whatever he did. I don't know how he actually did it, to be perfectly honest with you, but this is the light, and that's light. So these are photons, and that's two electrons. An electron is a back-to-back neutrinos. A muon neutrino is the black one, electron neutrino is the white one. And when they concuss at the Venturi, they actually can separate. The black one will not go through the Venturi if it is tuned correctly. That's the key. Rod just got extremely lucky. He was trying to make to do the double slit experiment, but he was using a single slit, and he used nails, which are rounded two round nails, like one right here and one right here. And when the particles hit, the black is too big to get through. The white sneaked through there and created all these showers. And that's exactly what CERN wants to see. And that's exactly what we delivered, is this. The black can't get through this slit. It's too big. I mean, too small. The black part is too big. The white can crunch down and slither through this little tiny slit. And because it's a Venturi, it forces them to concuss. It's not just like hitting a wall and having a little spray through it. It forces everybody to come together and squirt. And then at that point, the black ones just are too hard. They just can't. They won't concuss. They're exactly the same over here as they were over here, and they're coming right back. The white can concuss, and I can show you that too. So don't forget, muon neutrino, and I say that is dark matter. That's dark matter. It doesn't emit, it doesn't absorb, it doesn't reflect, and it doesn't compress. That's the new thing about dark matter. It does not compress. And that's why the white matter, which is the electron portion of the neutrino, has so much glow to it, but so much compression to it. They say is 85% of the universe is made of black matter, something like that. And the rest is the white particles, which are the energetic particles. That could very well be true. But I can tell you one thing for certain. The white one's getting through here, through the slit, and the blacks cannot get through. That I'm almost 100% certain of. And if you don't see it, I don't know how you're missing it. You see, this is why the white one can snake through that little tiny slit. You see, it can compress. It expands when it concusses with other particles. You can see that happening because it's going this way. That'll charge up and flip. The black ones just never change their size. They're the same size, the same, and the white ones apparently can squirt through like water through that little tiny slit. It's the only thing I can determine. If you have a different opinion, I'd like to hear it. Why? And the only time they show up like this is just prior to them smashing into that Venturi, and that's when they divide. These go slip right through, and these say, "Whoa, I can't make it." All right, now pay close attention to this. These are the particles coming in. Before they started to stack up and start glowing like this, you just really couldn't see them. They just were nothing. However, when they started to glow, now you can see them. Now they're emitting. So now we can see what they look like. And the only reason they're glowing is because of the concussion here against all the rest of the particles that are forced in from a Venturi. It just forces their fields, which are huge compared to the particles. The fields are gigantic. You saw them. Look at the size of them. These are the kind of fields I'm talking about. Absolutely enormous. And they're being forced into this Venturi. And at that point, the black ones just say, "I can't get through there." The white ones are going to go, but we're not going. And I'm going to show you this very, very close. Now, don't forget, this is a single slit. And just so you understand, it's going to be a Venturi here. It's something that goes like this, where everything has to force its way into that little tiny crack. The black ones won't do it. Here's what they do. Look. They say, "No, I'm not going. I'm not going." Only thing, 100%. 100%, not 99, not 99.9. There is zero whiteness here. Zero. You hear me? That starts with a Z and ends with a O. And these black balls are the dark matter, and they are the muons that were attached to the electrons uno momento ago, and then they just said, "Well, I can't get through there. But I do want to be with you guys. Let's get back together." And zip, right here. They show up again. They're all over the place. They want to get back in there. But at this point, everything's so explosive that they just can't get back together. Here, the energy value is dropping off enough where they can snap back together. And they do. And the patterns that are these interference patterns, they think that there's a flappy wave from here to there. This, don't forget, single slit, not a double slit. So there's no flap coming this way and a flap going that way like waves pushing against each other. This is a spinning disk of particles all through here, zillions of them. And then they want to stay away from each other. That's why they create these white stripes. And they say, "You guys stay that way, you guys stay this way." The white ones don't want to be next to each other. They hate each other. They just don't want to be next to each other anywhere, ever. You see them? They stay. You stay that way. You stay that way. Okay, we're good. And the other ones, the dark ones, say just as long as we can come along with you, we'll come along and we'll just hug up together at the end, and everything will be fine. And that's what happens. So that's the nature of the particles that make up literally everything. This is nothing more than two back-to-back electrons to create a photon. And then from there, everything is built. Atoms, nucleuses, and they're all made of dipoles. So there is no proton, neutrons to say. A proton is an uneven number of electrons. Okay, this basically proves what I'm saying about the nucleus of all particles are made of electron neutrinos and muon neutrinos attached together, which we would always call an electron. But in masses, they are dipoles. And you have a neutron and you have a proton. What's the difference between a neutron and a proton? The only difference is that a proton has one less electron than a neutron. So a neutron becomes neutral. So and I believe it's 1838, approximately, electrons make a neutron. 1837 becomes a proton, which is positive. It wants another electron to become neutral into a neutron. If a neutron sheds an electron and goes down to a proton, that's, again, it's only the neutrino it loses. And a neutrino is nothing more than basically what we always considered an electron, but it has a dark side to it. So I'm going to explain, well, I have explained pretty much what I had to say, and I'll take any kind of questions, and I can show my evidence. Let's just go through it one more time real quick. Now don't forget, here's what they're saying right here. A neutrino is a subatomic, smaller than an atom, particle, very similar to an electron. It is an electron, but it also has a muon attached. They say it has no electrical charge and a very small mass. It's the mass of an electron. It might even be zero. It can't be zero, obviously. Neutrinos are one of the most abundant particles in the universe. They are the universe. Every single neutrino is part of light or electricity or matter. That's all there is if they want to call them neutrinos, that's fine. Now, I do go back a long, long ways on this. This was 1970. I was just getting out of the military. I was in nuclear missiles and Nike Hercules missiles. And I went into physics, and at that point, this was my paper that you can see it's been around the block about 1,000,000 times. Back then there was no internet. You had to walk it around and show it to people. It didn't matter. Nobody paid any attention. So anyway, I got out of the whole thing and went into my own business, did other things. But everything was Coulombic forces. Everything was a dipole. Light is atomic vapor. This is some of the stuff I did. There's dipole interactions. That's all there was. And this is a statement I did, 1970. Transfer of energy is from light to atomic vapor. That's all there is. Light is atomic vapor. And I mean, I did a lot of this, so it's not. I didn't just do it one day and give up. I fought the law, and the law won. I had to go my own separate way, but that's okay. I am back. Okay, I told you when I make claims, I will make a claim, and I claim that that is a photon of light from a pulsed red laser, and I claim that that is dark matter and a muon attached to the white matter, which is the electron portion of the neutrino. Back to back, they make a photon. Photons bounce off things and create light. Electrons, which is only half of this, burn into things and they incorporate into things. All right, now, this is smashing into the Venturi. This is also my claim, is that these separate and the black and the white go their separate ways. The white goes through only if it's tuned correctly. And we need somebody to step forward that has resources. We don't have the resources to do this. This was 6-7 years ago, maybe more than that. And Rod tore this down. This was all what Rod Warren did this just by accident. Fabulous work. And stuck with this, and still doing it today. So it's time to recognize that contribution to this very important discovery. And I am saying that the Bohr model is no more. There's a new model. It's called a dipole, which is the plus and minus, black and white, electron flood theory, and it solves 100% of material interactions. Lightning, sprites, electricity, even the corona of the sun, and global warming is the scrubbing of our atmosphere into the atmosphere of space, which is nothing more than these particles coming from the sun as rays of light. They're particles. Those are electronic pushing, shoving particles. We should see them making things glow. We're scrubbing against them. An electron is nothing more than what they call the neutrinos, a muon electron neutrino, together. That's what an electron always was, and that's what does the work. The muon just follows along with it. A photon is back-to-back electrons. The glowy part makes the light, and the dark part pulls everything back together. A proton is, let's say, 1839 electrons. If you add one more electron to it, it becomes a neutron. That's all. And they know that. They say, well, you lose one little bit, and it becomes a proton. Well, that makes it charged, and it wants that bit back again. But as a neutron, it's neutral. All protons and all massive particles, and when we're dealing with light, we're only dealing with one particle, two particles. That's it. When we get into into atoms and nucleuses, just in a proton, we got 1,839 electrons, 1,840 in a neutron. But you're never going to see the black part. The black part will always be inside the white part, because the white part, as we saw, it just wants to get away from everybody else. So the white part will be always on the outside, being glued to the black part, which is on the inside. That's why we've never seen dark matter before. You have to break it apart to get into the dark matter, and that's what we did. We broke it apart. We broke the light. We broke the light. I think I showed you this. This is the progression of the wave, and then into the Venturi, the separation. The Higgs fields coming out, looking into the Venturi. We can see the Higgs fields start to manifest out here as they recollide. It's called Cherenkov radiation. These are the particles, and they start to manifest here. Black and white balls together, up and down. 2 electrons is my claim. And this is a reverse spinning particle. That little particle, I believe, was a reverse spinner. They're supposed to spin to the right hand and throw the particles out. This, I believe, spun backwards and collected its particle until it crashed with another Higgs field. I'm not sure. And this is blue, spinning to the right, drifting to the left, expanded down here, and concussing up here. So there's a lot to talk about that we have to display. So let's talk about it. Okay, so here we are, just yesterday. These record-breaking simulations of the universe aim to solve a tiny problem. What's the mass of a neutrino? Now, I showed you that these are neutrinos, and one of them, the white one, I am claiming is the electron neutrino, the black one is the muon neutrino. And that's simulation from CERN and from the rest of them. That's what they say it is. Now, how much does it weigh? Like most riddles, a solution might be found by thinking outside of the box. That's an electron. The two of them together make one, what we would consider an electron. An electron is 0.0000585 atomic mass units. I believe it's that. It's very, very tiny, but it has an energetic value. It has an impact. So let's discuss this.